The structure and chemical makeup of the core is critical to fiber operation. Optical fibers are divided into two broad categories, multimode and single mode. The major physical difference between them is the diameter of the core. Single mode fiber has a small core diameter compared to the overall fiber diameter. The small core size forces light to travel in a single path or mode down the axis of the fiber at a single wavelength. Multimode fiber has a much larger core diameter, allowing light to take a number of pathways from one end of the fiber to the other. The fundamental mode travels down the fiber axis, while higher-order modes will take a number of longer alternate pathways. When a short pulse of light is launched into the simplest type of multimode fiber, a step-index fiber, the fundamental mode arrives at the other end first, followed by the higher-order modes. This has the effect of stretching the optical pulse, which is called modal dispersion. This effect limits the usefulness of the fiber at high transmission rates when pulses begin to overlap and garble the information carried. The degrading effect of modal dispersion increases with fiber distance, so for this reason, single-mode fiber is the preferred choice for long-distance, high-bit rate transmissions, as it is not affected by modal dispersion. Very early, Dr. Charles Cow and others recognized that single-mode fiber was technically the best choice for optical transmission over long distances. In the 1970s, however, single-mode fiber was almost impossible to manufacture on a wide scale due to the technical limitations of the time. The precision required for splicing, termination, and even getting light into the fiber seemed impractical for field use. For this reason, research and development efforts were concentrated on multimode fiber to reduce the effects of modal dispersion. The original form of multimode fiber has a step-index construction, where the refractive index of the core is uniform across its diameter. This type of construction costs less to manufacture, but has the highest modal dispersion. To make multimode fiber more suitable for longer distances, Japanese researchers at Tohoku University invented the graded index multimode fiber in the late 1960s. Here, the refractive index gently tapers from low to high as you go from cladding to core centerline. Because light travels faster in lower index materials, the fundamental mode is slowed down, while higher order modes travel faster, so all modes will arrive at the end of the fiber closer together. This reduces modal dispersion. Multimode fiber is specified in micrometers with core diameter first, followed by the cladding diameter. The 50-125 fiber was the first type used by AT&T in 1977, and with its inherently high bandwidth, became the standard for laser-based telephone networks worldwide. In the late 1970s, however, lasers were still expensive and had major problems with stability, lifetime, and reliability. LED sources seemed to be preferable to lasers for use in the feeder portion of the subscriber loop, where the fiber and light sources would be present in relatively hostile environments. While 50-125 fiber had the highest inherent bandwidth, early connectors required larger core diameters. More importantly, a higher numerical aperture was required to transmit over 2 kilometers at 10 megabits per second. To more efficiently couple light from large spot-size LED sources, the 62.5-125 fiber was developed and became widely adopted throughout the 1980s and 90s in North America. However, 50 and 62.5 micron fiber have identical transmission length capabilities at 100 megabits per second. In the early 2000s, increasing bandwidth demands were driving the need for low-cost gigabit and 10 gigabit connectivity in local area networks, storage area networks, central office, internet, and data centers. Multimode fiber traditionally provided the lowest cost for short-reach, short-wavelength systems operating into the hundreds of megabits per second by allowing lower transceiver, connector, and cable termination costs. However, LED-based networks could not support gigabit per second data rates, requiring new low-cost lasers for multimode fibers. The availability of low-cost lasers in the form of vertical cavity surface emitting lasers, or VCSELs, provided a great incentive for system operators to increase the performance of their multimode networks. The advent of 850 nanometer VCSELs drove two fundamental changes in multimode fiber. The first was with manufacturing performance measurements. For decades, modal dispersion was characterized by overfilled launch bandwidth, a frequency domain measurement of pulse broadening which accurately predicted multimode system performance with LEDs. However, because VCSELs are lasers, they launched a restricted spot size into the core of a multimode fiber, exciting only the fundamental and low-order mode groups. An early lesson learned was that the modal bandwidth of a single fiber might be very different when coupled to an LED versus a VCSEL, in some cases several 100% different. A new approach to measuring modal dispersion was needed to understand a fiber's effective modal bandwidth, or EMB, with various light sources. The first attempt at characterizing laser bandwidth involved filtering an OFL bandwidth measurement through a 23.5 micron diameter fiber. The resulting launch excited low-order modes, but not the high-order overfilled modes, so the ensuing bandwidth measurement correlated well with 1 gigabit VCSEL performance. This new measurement became called Restricted Mode Launch Bandwidth, or RML bandwidth. With the introduction of the 10 gigabit Ethernet standard in June 2002, a new 50 micron fiber was introduced with a 2,000 megahertz per kilometer EMB, or roughly 10 times the bandwidth of legacy 62.5 micron fiber performance. This fiber was called Laser Optimized 50 Micron Multimode Fiber. Since VCSELs have a much smaller spot size than LEDs, and since gigabit Ethernet operational distances are limited by bandwidth, the higher bandwidth 50 micron fibers have become the preferred choice. The extraordinarily high bandwidth requirement drove yet another change in measuring EMB. As mentioned previously, traditional bandwidth measurements involved a quantification of pulse broadening in the frequency domain. In order to understand high-performance fiber EMB, manufacturers employed a familiar tuning tool that measured differential mode delay, or DMD. DMD is a measurement of pulse broadening between individual mode groups in the time domain, where modal dispersion is quantified in seconds rather than cycles. This hyper-accurate measurement gives a roadmap of a fiber's modal dispersion, which can then be mathematically translated back into EMB for any standards-compliant VCSEL. One method of translating DMB into EMB is to apply a set of 6 templates, or DMB masks, to the relative delay between the mode groups. If the differential modal delay falls within any of the masks, then the fiber passes the required minimum of 2,000 MHz per kilometer. An alternate method of translating DMB into EMB is to consider differential delay and attenuation from the DMB instrument to mathematically reconstruct the output pulse shape for a range of permissible VCSELs. Bandwidth on each fiber is predicted with 10 sources, and the minimum calculated bandwidth is assigned to the fiber's performance. This method is called the Minimum Calculated Effective Modal Bandwidth, or MIN-EMBC. Both MIN-EMBC and the DMB masks were adopted by standards as alternate predictors of 2,000 MHz per kilometer EMB with 10 gigabit VCSELs. Improved EMB measurements were only the first change to multimode fiber following the introduction of 850 nanometer VCSELs. The second improvement was to optimize the fiber's bandwidth towards the more cost-effective 850 nanometer window. Since legacy fibers were originally used in long wavelength networks, 50 and 62.5 fiber peak bandwidth capabilities had traditionally been centered around 1300 nanometers. A fiber's peak wavelength performance can be shifted by changing the shape of the graded index profile. We know that glass refractive index is a ratio of the speed of light in a vacuum to the speed of light in the material. In fact, the refractive index value of glass changes slightly with wavelength. For example, the refractive index of silica is 1.452 at 850 nanometers, but 1.447 at 1300 nanometers, meaning the light travels a little faster in glass at 1300 nanometers. This also means that when designing a graded index profile which is intended to slow down the fundamental mode to match the velocity of the higher order mode groups, EMB can only be optimized for a single wavelength, with a lower effective bandwidth for all other wavelengths. Therefore, new fibers with 2,000 MHz per kilometer EMB at 850 nanometers required shifting the peak wavelength away from 1300 nanometers. Such fibers are commonly available today for installation in high-performance enterprise networks. Meanwhile, in the midst of multimode fiber technological progress at 850 nanometers, all standards-based fiber specifications continued to maintain 500 MHz OFL bandwidth at 1300 nanometers, ensuring performance with legacy protocols and bit rates. Even newer protocols, such as the gigabit and 10 gigabit Ethernet standards, offer an alternative functional solution using 500 MHz OFL bandwidth at 1300 nanometers. These long wavelength solutions most often use single-mode lasers, like a Fabry-Perot laser that has a very small spot size. In order to keep from focusing such a large amount of energy on the fiber center line, standards typically require a mode conditioning patch cord, which physically offsets the transmitter's launch into the intermediate and higher order modes. Such solutions are typically higher cost than the 850 nanometer technologies, but offer an upgrade option for network managers, with an installed base of 62.5 or 50 micron multimode fiber. Multimode cables are widely available with maximum attenuations of 3.5 dB per kilometer at 850 nanometers and 1.5 dB at 1300 nanometers. Fiber attenuations can be slightly lower.